All right, let's talk about a math problem. So simple a kid could get it, but it stumped the greatest minds for decades. It's this tiny little puzzle that kind of pushes the limits of what we even know about numbers. We're going to try and unravel this thing together.
And no, that's not just for dramatic effect. This is a problem that mathematicians literally warn their students about. They'll say, don't even try it. Don't waste your career on this. Why? Because it's like a black hole for your brain. It'll suck you in, and you might never come out with an answer.
So what is this thing? Officially, it's called the Collatz Conjecture, but it's got a bunch of other names too. The 3n+1 problem, Ulam's conjecture, you get the idea. Each name is kind of like a clue left by another mathematician who got obsessed with it. And what got them hooked? This one simple, almost silly idea that if you take any positive whole number, any number, it will always end up in this little loop, 4, 2, 1, every single time.
So, why dangerous? What's the big deal? It all comes down to two super simple rules. Let's get into it.
Seriously, that's the whole thing. If your number's odd, you do one thing, multiply by 3 and add 1. If it's even, you just chop it in half. And you just keep doing that over and over again to whatever number you get next.
Okay, let's try one out. How about the number 7? Seems simple enough. Right, so 7 is odd. What's the rule for odd numbers? We multiply by 3 and add 1. And that brings us to 22. Okay, new number. 22 is even, so now we use the other rule. Just divide it by 2.
Which gives us 11. And here's where things start to get a little wild. We're just going to keep this going, right? 11 is odd, so boom, it shoots up to 34. 34 is even, so we cut it to 17. And from here, well, the ride gets even bumpier. I mean, look at this thing go. From 17, it leaps up to 52. Then it gets chopped down. 26, 13, then back up to 40. It's like a roller coaster. But eventually, it all comes tumbling down. 8, 4, 2, 1. And once you're at 1, you're stuck. You're in the loop. The whole mind-bending mystery is that every single number we've ever tried does this.
But as you saw, the path is chaotic, right? It's not a straight line. So mathematicians started digging, trying to find some kind of order in all that madness.
Yeah, they have a great name for these sequences, hailstone numbers. And it's such a perfect description. Think about a hailstone forming in a cloud. It gets shot way up high, then falls, then gets caught in an updraft and shot up again. Over and over. That's exactly what these numbers do. They skyrocket to crazy heights, then crash down, all before they finally hit the ground at 1.
And if you want to see just how chaotic it is, look at this. We've got two numbers, 26 and 27, right next door to each other. For 26, the journey is super quick. 10 steps, it hits a high of 40, done. But 27? Oh my gosh, it takes 111 steps to get home, and on the way, it climbs all the way up to 9,232. That's just insane for two numbers that are practically the same.
But here's the weird part. In all of that total chaos, there's a ghost of a pattern. If you take all the numbers in one of those long, crazy sequences and just look at the first digit of each one, they follow a rule called Benford's law. What does that mean? It means about 30% of them will start with a 1, and almost none of them will start with a 9. This is a pattern you see in real-world data, like stock markets or river lengths. So what on earth is it doing here? It's so strange. It feels like there's some deep structure we just can't see.
Finding weird patterns is cool, but it's not a mathematical proof. To really settle this, you have to do one of two things: prove it's always true, or find one single number that breaks the rule. That's the hunt for the counterexample.
And there are really only two ways this whole thing could be wrong. The first possibility? There's some number out there that starts a sequence that just goes up forever. It never comes back down, it just flies off into infinity. The second possibility? There's another loop. A totally different cycle of numbers, somewhere out there that has nothing to do with our 4-2-1 loop. If we find either one of those, game over. The conjecture is false.
So, have we found one? Well, people have been looking, and I mean really looking. We've thrown pretty much all of our computing power at this.
Get ready for this. Computers have tested every single number, up to 2 to the power of 68. That number is 295 quintillion. And you know what? Every single one of them, every last one, fell into the 4-2-1 loop. We haven't found a single exception.
So, we're done, right? It must be true. Well, maybe not. Take a look at this. There was another famous problem, the Collatz conjecture, that everyone thought was true.
They checked tons of numbers, but the first number that broke the rule was found way out at around 10 to the 361st power. The number we've checked for Collatz, it's not even a grain of sand on the beach compared to that. So brute force alone might not get us there.
But we have had a huge breakthrough recently, and it came from an absolute genius, a mathematician named Terry Tao. In 2019, he managed to prove, like a real mathematical proof, that almost all of these sequences do in fact get smaller. It's not the final answer, but it's the closest anyone has ever come.
But hang on, almost all? What does that even mean? It sounds a little bit like a cop-out, right? Well, in math, it means something very specific.
Let me give you an analogy. Think about perfect squares, 4, 9, 16, 25. If you look at numbers from 1 to 100, 10% of them are perfect squares. But if you look from 1 to a million, that percentage gets tiny, just 0.1%. As you go toward infinity, the percentage of numbers that are perfect squares gets closer and closer to 0. So mathematically, you can say almost all numbers are not perfect squares. But does that mean perfect squares don't exist? Of course not. There's an infinite number of them. And that's the catch with Aussie's proof. It's a landmark, for sure, but it still leaves the door open for an infinite number of weirdo exceptions.
Which brings us to the final, and maybe the most disturbing idea. What if? What if there is no answer? What if the problem is literally unsolvable?
Check this out for a weird clue. If you do the exact same process but with negative numbers, you don't just get one loop, you get 3 of them. 3 totally separate cycles that have nothing to do with each other. So why? Why would the negative numbers be this complicated, but the positive numbers are all supposed to fall into one neat little package? It's like a hint that there's something bigger going on here that we just don't get.
This leads to the big question, could this problem be undecidable? This is a real concept in math. The mathematician John Conway proved that for problems like this one, it could be logically impossible to ever know the answer. Not just that it's hard, but that a proof simply doesn't exist. The question itself might be broken, and it's possible the Collatz conjecture is one of these.
And that's where we have to leave it. The famous mathematician Paul Erdős once said about this problem, mathematics is not yet ripe enough for such questions. And maybe that's the real answer. Maybe the problem isn't the puzzle. Maybe the problem is us. Maybe our math just isn't powerful enough yet to understand something so simple. It's a mystery that's still out there, waiting for someone to finally crack it.